Welcome ENET 130 at Bellingham Technical College. This is our study of semiconductors, and this is our third recorded lecture in our Fiore Chapter 4 textbook section on bipolar junction transistors. When we left off at the end of the last lecture, we had introduced the Ebers-Moll model for DC treatment of bipolar junction transistors. So we took our three-layer semiconducting sandwich of a semiconductor device, which is the transistor, and we represented it with something that's much easier to deal with in a circuit. And just to review here, we use an ideal current source between the collector and the base, and that is going to give us a collector current that's equal to the base current times our transistor beta, our current gain factor. And we use an ordinary diode between the base and the emitter. And the forward bias voltage of that diode is going to depend on the exact nature of the semiconductor, but generally speaking it'll be 0.7 for silicon. Okay, now we are going to put that to work in a real simple amplifier circuit. So we're looking at current gain, so we're going to amplify the current that we can flow through the circuit. We're going to put a little current signal into the base of our transistor, and we're going to look at the effect that that has on the current that's being supplied by our collector supply and flowing through the collector resistor R sub C. Okay, so to do that we're going to start by replacing everything here with our Ebers-Moll model. So here's our model representing our transistor. Collector base, there's our diode, there's our emitter connection. I'm just putting it into a little dotted circle so we remember that this is the transistor itself. Okay, and we have the voltage from collector to emitter, the voltage drop over the whole transistor from the collector to the emitter is our VCE, and we have no idea what that is at this point. We're going to find it when we do our Kirchhoff's voltage law loops and solve for it by difference. We do know what the base to emitter voltage difference is, and that's a 0.7 volt drop going from the base to the emitter because we are going to overcome a forward bias voltage going through that diode. Okay, I have transposed the values, from example 4.2. So we're actually going to solve for collector current and voltage drops over things in our circuit, which is actually a little amplifier circuit with these values. So I've got them already drawn on our example. So we have a base voltage supply VBB of 10 volts. We have a 200,000 ohm base resistor. These tend to be pretty darn big because you don't want a lot of current going into the base. Remember, that's your signal current, so it only needs to be itty bitty to control a much greater current coming through the collector emitter. And to that end, our collector resistor is only 1K because we're going to flow a lot more current through here. We don't want to be dropping too much voltage. And we have a collector voltage supply VCC of 15 volts. The emitter we've hooked straight to ground. So we're going to start with this is a hint, always start with your base emitter loop. Why? Because the base to emitter junction is something you know. We're going to take a 0.7 volt drop going from B to E. We have no idea what VCE is, and so if we don't know IC and we don't know VCE, we can do a Kirchhoff's voltage law loop through the collector emitter here, and we're going to do it. But at this point it'll have two unknowns in one equation. So we can't really solve for what we want. But we should only have one variable in our base emitter KVL loop, and these long curvy arrows are our Kirchhoff's voltage law loops. So I can write a Kirchhoff's voltage law expression for a path that goes from ground. We raise our voltage up 10 volts as we go through the base supply. I'm going to drop my voltage by 200,000 ohms times I base. Then I'm going to drop my voltage again, 0.7 volts, getting over the forward bias of the base emitter junction of the transistor, and that's going to take me right back to ground. So I can tally up all those voltages. We're going to go up 10 volts through VBB, and then we're going to go down 200K. That's 200,000 ohms times I base. And then we're going to drop another 0.7 volts going through the base emitter junction, and that's going to take us back to zero, back to ground. 0 volts. Okay, so that's one equation that I was able to write by applying Kirchhoff's voltage law through the base emitter path. Started at ground, raised voltages, dropped voltages, and came back to ground. So I can solve that for I sub b. You can just do a little algebra and solve it for I sub b. And I won't do that here in the lecture. I'll scan down to look at what Mr. Fiore did. I'll let him do my math for me. But you can see he went through the same steps. We would have ended up getting this expression. So 46.5 microamps. So 46.5 times 10 to the minus 6 microamps. Okay, now I'm going to use that and a characteristic of my transistor to give me I sub c. Then I'm going to use that to get everything else I might want to know, including the voltage drop between the collector and the emitter, looking at the transistor as just a single component. So I'm going to write my expression for collector current as it depends on the transistor itself. If we're not limited by anything else in the circuit, my collector current is going to be the transistor beta times I sub b, the base current. So this is my gain. So chances are beta was pretty big. Let's see what we were given, 100. So I know my collector current, again, if it's not being limited by something outside of the transistor, which is a case we're going to look at next, but if the transistor is the thing limiting our collector current, all I have to do is multiply this times 100. So this is 46.5 times 10 to the minus 6. That would be 46.5 times 10 to the minus 4. And check that. So that ends up being 4.65 milliamps. A lot more, 100 times more, exactly. There's our current gain. So we used microamps to control milliamps. So there's our scale of control. Now what if we wanted to know what the voltage drop was between the collector and the emitter across the transistor itself? I mean, it's a circuit component. We might want to know how much voltage it's dropping. Well, here's where we pull out KVL for our collector to emitter path. So we're going to go from ground. We're going to raise ourselves up 15 volts going through the collector voltage supply. We're going to drop 4.65 milliamps times 1K. Wow. There's some easy math. 4.65 times 10 to the minus 3 amps times 1 times 10 to the third ohms. So I'm gonna drop 4.65 volts. So I'm down to just a bit over 10 volts, and then I'm going to drop the collector emitter voltage, whatever that is, and oh, I'm down at ground. So I could write that as 15 volts. And we have a little bit of messy effects with our drawing program. But we'll try to draw as neatly as we can. Minus I sub c times R sub c minus whatever VCE is equals 0. And that's not a magic formula, that's just Kirchhoff's voltage law being applied from ground, raising voltage going through this supply, dropping voltage DC over a resistor, good old Ohm's law, and then saying, hey, I have to get back down to ground, so the remaining voltage that I didn't drop over here must be dropped over the transistor. I just solve it by difference. And I've got this value here. I was given R sub C, so I can just solve for VCE. So we're going to hope it's going to come out to a little bit over 10, which it was. So that's the real easy way that we can use our Ebers-Moll model of a transistor, of a bipolar junction transistor. Kirchhoff's voltage law applied first to the base, where we know our voltage drop going through the transistor, it's just that base emitter junction, and then applying it to the collector to emitter path, and Kirchhoff's current law, making sure that our current going in or out of the base adds up to currents going in and out of the collector. They all have to add up. If we need to use beta to solve for a collector current based on our base current, we can do that if we have beta. We can assume a beta if we need to. But we're going to see next that there's some cases where the external circuit doesn't let us get all the way to beta. And that is a special case of the transistor operating in what is called saturation. Okay, we had a slight pause after we finished our first example of applying the Ebers-Moll transistor model to a real amplifier circuit and solved for our base current, our collector current, and we solved by difference for the voltage drop going across the transistor itself, current to emitter. So we now know the voltage drops and currents, so everything in the circuit. Okay, we did also at the same time mention there might be some instances in which we don't want to use beta to control the collector current. We might want to design the circuit outside of the transistor such that it limits the collector current instead of beta. Now, the first question you might ask is why? We went to a lot of trouble to get this magnificent little semiconducting device that has this enormous current gain. Why would we want to throw it away, or any part of it? And the answer is beta is not very stable. When we read our spec sheet, we noticed that for any given transistor, our beta, especially in the area where beta is high, in the right collector current and temperature range, it can vary, and it also varies with temperature. So you can build your circuit and start flowing some big collector current within spec, of course, but it's still going to cause a little bit of heating. You can suddenly get a higher beta, which might cause more current to flow through, which causes more heating, and you've got a positive feedback loop, which can end up destroying your circuit, or at the very least giving you more current than you had planned on. So we're going to look at some circuits in which collector current, which is approximately equal to emitter current, is being limited by not just the transistor beta. We're not going to use quite all of the collector current that the beta would give us. And in looking at those cases, we're going to define something that's called a DC load line. And this is another plot of collector current versus collector emitter voltage drop over the transistor. But unlike the ones that we defined earlier up, and I'll just scroll right back to them, our sets of characteristic curves here. When we first defined transistor collector current versus collector emitter voltage drop, when we just kind of defined how a transistor works, these are specific to the device. We can also plot collector current versus collector emitter voltage drop for the whole circuit, and that's what a DC load line is. So it's a plot of literally of collector current versus a collector emitter voltage drop, but it takes into account everything in the circuit, all of our supply voltages, our resistors, everything operating on the transistor and the external circuit, and it ends up being a straight line rather than those characteristic plots. And the operating point of the transistor in particular is going to depend on beta, but the intercepts that actually define the line are going to be a function of the external circuit. So this is an example of a DC load line, and the easiest way to get it is to go back and look at the extreme examples of what would happen in our circuit. And to do that, I'll go back to our simpler model, which we haven't marked all up here a little bit. So we'll mark our VCE here. And we have some collector current flowing, and we have very little base current, so I sub C is approximately equal to IE. So here's our collector emitter voltage across our transistor. So we could write our Kirchhoff's voltage law expression for collector current. We're gonna wing it. Minus VCE R sub C. So if we go from 0, we go up VCC. We're going to subtract I sub C times R sub C. So if we multiplied by that, we'd subtract it from this side. We're going to subtract V sub E and get down to 0. Okay. So if I rearrange terms from a Kirchhoff's voltage law expression of voltage going on this path, and then rearrange my math, I could get this expression for collector current. Okay, this is part of the external circuit, VCC, and so is this. And here's my mysterious collector emitter voltage. And this is a line equation. If I had the Y and this is X, I could rearrange this to look like a line equation. So I could say my Y, because I'm going to plot collector current on the Y-axis, equals negative 1 over R sub C, there's my slope, times my VCE, plus, just rearranging the math. I applied Kirchhoff's voltage law to the collector emitter path. I got an expression and then I rearranged it R sub C. So I'll erase this part. Okay, so now I got a line equation, and I can use that to plot collector current versus collector emitter voltage. An imperfect eraser. Okay, so this is on the y-axis. Here's my x variable, and here's my my y-intercept. So I'm going to end up with something where this is here, and VCE is on. Okay, so let's think about how to plot a line equation. I'm going to label my y-axis, as we should all do. Okay, so collector current versus collector emitter voltage drop. When VCE is 0, this whole term is 0, and my collector current is equal to the supply, the collector supply, divided by R sub C. So that's this point here. And that's where VCE is 0, because this is the origin. Okay? If current was 0, if I sub C was 0, I could take this term, move it over there, multiply by R sub C, cancel out the negative signs, and I would actually get VCC. You could do the math for yourself just by setting I sub C equals 0. So that gives us this point down here. So every other point in between, if VCE was somewhere in between 0 and the collector supply, it would plot somewhere along here, and the corresponding I would plot somewhere in this range, and we would get a line. So anywhere the transistor is operating in this particular circuit, we're going to have a collector current and collector emitter voltage drop that sits somewhere on this line. We can never get more collector current than we would if VCE was 0. Say the transistor was operating somehow that had no voltage drop over it at all. It was magical. It broke the second law of thermodynamics somehow. Well, in that case, the collector current would only be limited by this resistor. That's the maximum collector current you can deliver in this circuit. It doesn't matter if your beta is 10 million, because R sub C and VCC are limiting I sub C. It doesn't care what the transistor is. The best the transistor could do in terms of not getting in the way and not limiting I sub C is to have a 0 voltage drop over itself. So if that is called operating in quote-unquote saturation, and all it means is the external circuit, not the transistor beta, is dictating our I sub C, and that means we're operating at this point right here. Likewise, we could have a condition where the voltage drop over the transistor is huge and we don't get any collector current at all, and that's this point, and this is known as the cutoff point. So we got some more vocabulary having to do with transistor operating points, but this is the transistor and the circuit working together. The plot lines that we saw that go on a spec are the transistor characteristics alone. So this is cutoff, this is saturation, and they're both dictated by really the collector emitter path and in its KVL expression. So what you choose for supply voltages and resistors flanking this, it's not controlled so much by the base, but our collector and emitter resistors and our supplies will dictate this. And then if we want to operate the transistor somewhere in between, then its beta is playing a role. If it's operating at some point in between, and the particular collector current and collector emitter voltage drop pair that makes up that point has a special name, and it's called the Q point. And that says that's the collector current and collector emitter voltage drop for that particular set of operating conditions, and that is dictated by your transistor beta. So we can be controlled by the circuit or we can be controlled by the beta, and it depends on how you build your circuit. So here's a little bit neater drawing of the one that we just derived for that same set of conditions with IC sat, where the transistor is in saturation, and our cutoff current emitter voltage drop that corresponds to cutting off. It's so big we can't get any collector current. Okay, an actual transistor operating point is your Q point. And of course we have a special name for the VCE at the Q point is VCEQ, and the collector current at the Q point is ICQ. So more vocabulary, which is important when we're discussing our circuit performance with other engineers and other technicians. Okay, all possible operating points lay on this line for that circuit. If you change a resistor, you change a supply voltage, you're gonna change this line. You'll have a new line that you can follow. Okay, here's the way a couple of different betas would plot. If we change the transistor or we changed its temperature, we would have a different beta. So endpoints controlled by the external circuit. Which Q point we're operating on is going to then be dictated by the transistor beta. And we can go through some math and we can show how that is the case for a given circuit and a given transistor. But this is what is known as a DC load line. So it includes everything that any transistor beta can do within the limits of an external circuit that you've designed for it. Okay, let's put all of those concepts to work and let's look at how transistors can be used as switches. And when we're looking at what's called transistor switching mode, we're looking at cases where we're not throttling the current, we're not necessarily having our beta controlling what we're doing. We're going straight up to saturation where the external circuit is what is controlling. And in that case, basically the transistor turns on all the way up to IC sat or it's off. And that's very useful if we need to control current in an on-off kind of manner, known as a saturating switch. Okay, so here's an example of one. And there's several examples, and in fact the rest of this chapter, chapter 4, basically deals with different combinations and instances where we have beta control or we have external circuit control, and looking at what it takes to turn a transistor on or off based on our, pun intended, base current, and whether or not our base voltage is high enough to achieve that forward bias, usually 0.7 between the base and the emitter. So we'll see a lot of examples, and I'll go through some of these quickly. I'm not going to write them all out. We have lots of practice problems at the end of this chapter that you can do and refer to, and depending on which class you're taking, your instructor may or may not have some written examples. I know I provide them when I can. So just the highlights here. So here's an instance where we've got an LED and we want to control the current through it. We want to turn it on and off, and we have what's called a logic input. Now, a logic input is nothing other than just a voltage signal, and it's binary. It's between two levels, high, low, on and off. But the defining characteristic of a logic signal is it's very low current. It's coming from a special type of circuit you'd use in your computer. It's not a power circuit. So we can't really do much. The current that would be coming in on that logic input wouldn't be enough to make the LED really illuminate much. Remember, LED illumination is a function of the current flowing through it, so it wouldn't even be enough to let the LED glow. But it's what we've got. It's probably the signal being produced by a microcontroller or something. So what we need to do is amplify the current faithfully in a way that we can show the LED is on only when our logic signal is high or low. So let's walk our way through our transistor. To open the transistor and to get current to flow from the collector to the emitter, we need to make sure that we can get our base to our emitter potential being more than 0.7. So if we look at a voltage signal we would have to have here, say it was 0 volts here, and 0 volts at ground, there's no way that we can overcome our forward bias voltage between our base and our emitter, and so no current would flow through the transistor collector to emitter. It's off like a switch. If we supplied a voltage here at the logic input that was high enough that after we flowed a little bit of current into the base, dropped whatever we're going to drop by Ohm's law over the base resistor, we were still more than ground plus 0.7 volts here at the base, we could turn the transistor on, and then we could determine how much collector current is going to flow via either our the constraints of our circuit here, or using our beta relating our base current to our collector current, our beta gain. So we're using a very small base current coming with the logic input to control a much bigger current that's big enough to make the LED illuminate. So in looking at how much current this external circuit can give us, we can just kind of walk our way up a KVL loop. We could start at 0, and going in this direction we're going to go up whatever that mysterious collector emitter voltage is, and then we're going to go up by the voltage drop over the LED, then we're going to go up by IC times RC, and then we're going to get to the collector supply. So that's how we would kind of set up our KVL loop in that case. So here's another one where we can, another arrangement, but this time we have a PNP transistor because we want to flow current the other way, so that's handy. They come in both flavors. So this time here's the emitter base junction, and in order to open it, we're gonna drop 0.7 volts going from the emitter to the base because current's flowing the other way. So whatever the emitter voltage is, we're going to subtract 0.7 volts and get to the base, and current's going to flow in that direction. So in this case, the logic input is going to have to be low. It's going to have to be less than the emitter minus 0.7 to have current flow out the base, which will open the transistor, and then we can flow the collector current. And in this case, we actually can get a gauge of what the collector current might be looking up our KVL point up here to our collector emitter start. But in either case, we would have to make some assumptions about the collector emitter, probably using our beta, because we don't know if we're at saturation or not in both cases. Okay. Here's another example. We're asked to determine what current will turn the LED on current, or what current will be flowing through it when it's on in the circuit. And we're going to assume that we get 5 volts at our logic input as a turn-on signal, and that our voltage drop over the LED is 1.8, which is pretty typical. It's probably a red one. And that we're operating at saturation. So no voltage drop collector to emitter over the transistor. So we can set up a couple of KVL loops, which I've done and written them out for you. And we can find, just going through KVL and solving for I base, we get just a little under 1 milliamp. But since we know that the collector emitter voltage is 0, we were told we're operating in saturation in this case, we really didn't need to use that I base. And we'll find that chances are our collector current is going to be quite a bit less than what we would expect to have a beta controlled collector current. We would expect that to be something like 92 milliamps if we multiplied by 100. In this case, we're controlled by the external circuit. So we're going to have 5 volts minus collector current times 330 minus 1.8 equals 0, because we were told that there's no voltage drop over the collector emitter. So if we solve for I sub c in that case, we get just 9.7 milliamps. So we're operating way over. We're actually operating at saturation. So up at the upper end of our DC load line. So we either have to use our beta, or we have to know something about the collector to emitter voltage drop. Okay, another just a neat example of using transistors is switches. Remember, they're great for allowing little bits of current to control bigger amounts of current. So this is an example of almost a cascading three-way switch. We've got a really tiny current voltage signal coming out of a microprocessor. It's going to be applied to the base of our transistor, and when it is big enough or in this case big enough, to overcome the base emitter junction voltage. The transistor turns on and we flow a current from our supply. Then it in turn is enabling a solenoid, which perhaps is actuating a relay, can turn a motor on. So very small current controls somewhat larger current, controls ultimately very large current. And that cascading small to large current is very characteristic of how you will design and troubleshoot switches in an industrial setting as an electronics technician. And the rest of the examples in this chapter are just more variations on the same, looking at different ways we can apply Kirchhoff's voltage law between collector and emitter, with some previous knowledge about our collector-emitter voltage drop, or using a beta and a knowledge of the base current, usually given to us via a base emitter Kirchhoff's voltage loop and our understanding of the base emitter junction voltage. So this is a warning. VCE is not always zero. Transistors don't always operate in the saturated state. They'll only do so if you've got circuit elements in the collector emitter path that limit the collector current more than what beta would otherwise permit. So we just apply Kirchhoff's voltage law and what we know about the base emitter junction, and we let the circuit tell us where it's operating, basically. But we can always define those endpoints of the DC load line by basically assuming either zero collector current or zero collector emitter voltage. So we can at least define the endpoints. So we have another example here where we have an input, and then we can solve for our base current if we want. So we have whatever our voltage is here, minus 0.7 minus the emitter current, which will be approximately equal to the collector current, times 270 equals 0. So that's KVL number 1. And then we've got 10 volts minus our LED voltage, which is 1.8. So we are at the collector with, entering the collector with 8.2 volts. We have the collector emitter voltage drop, and then we have a further reduction to ground by the collector current times 270. So in this case, chances are we're somewhere in the middle of the load line. There's no reason to necessarily believe collector emitter voltage is 0. We could use our beta and see what we have and calculate it that way. So in this case, we'll step through it. Excuse me, let's widen that out so we can see all of our calcs. Okay, so let's see if we needed to use beta. We have VCC 10 volts minus 1.8 minus the collector emitter voltage drop, whatever it may be, and minus I emitter, whatever that would be, times 270 equals 0. And in this case we solve for a VCE equals 3.9 using an emitter current that we got, no doubt, from using our beta. Let me pause this really quick. Need to give that a quick check. Quick correction. Pardon me. We had to use our emitter current way back in our base emitter loop. A million pardons. We didn't have a base resistor, so we didn't have a voltage drop due to the base current. We really didn't care what it was. So we knew what the base voltage was because our logic input was the base voltage. So we had the base voltage minus our base emitter voltage drop for our forward bias junction, 0.7, minus 270 times the emitter current, which we know later is the collector current. So we got our I sub C or I sub E straight out of our base loop. And so we used the base KVL, but we didn't need beta because we didn't have a base current to worry about in this case. So we only had one variable in that case. So we had what we were told is a 5 volt input, which is the base voltage, minus the base emitter junction, minus the voltage drop over this 270 ohm emitter resistor, takes us back to ground. So we solve for I emitter, and since we know I emitter and I collector are approximately the same, we could put it right into our collector emitter KVL, and we could solve for the collector emitter voltage drop. So we have a Q point. We're operating at 3.9 volts collector emitter voltage drop and 15.9 milliamps. So we're partway along the load line. Lots of ways we can apply a base voltage. So in this case, in all of our examples so far, in this case of figure 4.24, we just applied a base signal, and so we could open the transistor by applying a signal that would overcome our base emitter forward bias junction voltage, or not, and in which case no current would flow through the transistor. So there's a lot of ways that we can relate the voltage at the base to the voltage at either the collector or emitter and create a bit of a relationship between them. So we create a little bit of a feedback scenario, which can be super useful. And there's lots of examples of ways to do that, but one that Mr. Fiore goes through is what's known as a Zener follower. And in this case, we can imagine we have the collector over here on this end, and we have a collector to emitter current flowing, and we can siphon some of that current through this resistor. And if this output point is above the Zener reverse breakdown voltage, we can have it flow. But by having the Zener here, we ensure that this point, which just happens to be the base voltage, is now related to ground and to the Zener breakdown. So we can apply what's effectively a constant base voltage going in and basically have that relationship there and still have some current that we can flow into the base at a particular voltage. So the input signal is going to be pretty much equal to, it will open the transistor if it's equal to the Zener potential minus the forward bias voltage necessary to get across here, as this is already at a fairly high potential. So we have to be our 0.7 volts above this to open it. Okay, that was the last example, and that's a little bit of an example of effectively some signal dependency, not quite feedback, but all related. So major takeaways: transistor will only conduct current between the collector and the emitter if we have overcome the forward bias voltage at our base emitter junction, and when we do that, we are by definition flowing a little bit of current into the base. Our collector current, if it is not constrained by other things in the circuit, will be related to the base current by our beta. IC equals beta times IB. But we can construct a circuit such that our collector current doesn't ever reach its full potential of what the transistor could supply by beta, by having other resistors and supplies that effectively limit that. And that is a good thing sometimes, because betas can shift with temperature and with collector current and then create an unstable situation. Otherwise, when we're analyzing our circuits, we really have to fall back on our basics. We have to understand how other semiconducting components work, like this Zener. We have to know that this point is going to be the Zener breakdown voltage above whatever ground. We have to follow our Kirchhoff's voltage law loops very faithfully and mark out the points if we need to. And remember that Kirchhoff's current law always applies to a transistor. So the sum of the currents in the base emitter and collector have to add up. So at this point, this is the end of the lecture, and I would very much recommend that you go to the end of our chapter 4 and work as many of the problems as you can. These are very simple concepts, but it is really easy to get tangled up, subtract things when you need to add them. Please do a lot of practice, and you'll find that this comes naturally, and you get kind of an intrinsic feel of how transistors work in what is effectively a simple amplifier circuit. And then we can build on it to do what you truly took electronics to do. So we'll see more of that next time.